Welcome to the heart of process automation, analog signals and scaling. Think of analog signals as the nervous system of any process plant. They carry vital information from field instruments to the PLC and SCADA systems, ensuring every part of the plant communicates seamlessly. But a single error in translating these signals can lead to catastrophic failures. In this chapter, we'll break down the math, practical procedures, and troubleshooting steps that keep your plant running safely and efficiently. Let's start by understanding what the PLC actually sees when it receives an analog signal. When a field instrument sends an analog signal, such as 420 EMA, the PLC doesn't see a temperature or pressure value directly. Instead, the analog input module converts this signal into a raw integer. For example, in many ABB systems, 4 MA might correspond to a raw value of 0, and 20 MA to 27,648. However, it's crucial to check your specific module's configuration, as some systems use different multipliers. This raw value is the foundation for all further calculations and must be understood before any scaling can be applied. Operators don't work with raw integers. They need real-world units like bar, degrees C, or percent. These are called engineering values. The process of scaling transforms the raw integer from the PLC into these meaningful units displayed on SCADA screens. This conversion is essential for operators to monitor and control the process accurately. Without proper scaling, the data shown to operators would be confusing and potentially dangerous. The core of analog signal processing are the scaling formulas. For analog inputs, the general linear scaling formula is used. Engineering value equals the difference between the raw value and its minimum, divided by the raw range multiplied by the engineering range plus the engineering minimum. This formula ensures that every raw input is accurately translated into real-world value, making the data both reliable and actionable. Reverse scaling comes into play when the PLC needs to send an analog output, such as controlling a valve position. Here, the engineering value, like 65% open, must be converted back into a raw integer to generate the correct 420 MA output. The reverse scaling formula mirrors the input formula, ensuring that the control signal sent to the field device matches the operator's intent. Accurate scaling is not just a mathematical exercise, it's critical for plant safety and efficiency. If scaling is off, operators may misinterpret process conditions, leading to incorrect decisions or even equipment damage. Proper scaling ensures that every value on the SCADA screen truly reflects what's happening in the field. Analog signals in the field are rarely perfect. They're often affected by electrical noise, process fluctuations, or even environmental factors. This noise can cause control loops to behave erratically, making it difficult to maintain stable operations. That's why filtering and deadband settings are essential tools for every automation engineer. To smooth out noisy signals, a first-order exponential filter is often used. This filter applies a time constant to gradually adjust the signal, reducing the impact of sudden spikes or drops. Guide recommends different time constants depending on the instrument type. 0.510 seconds for clean pressure, 2.050 seconds for pulsating pumps or RTDs, 5.015 seconds for ultrasonic levels, and 5.030 seconds for notoriously noisy pH signals. Deadband or hysteresis is a setting that prevents alarms or control outputs from toggling rapidly when a signal hovers near a limit. For example, if a high alarm is set at 80 degrees C with a 2 degrees C deadband, the alarm turns on at 80 degrees C but won't turn off until the temperature drops below 78 degrees C. This prevents nuisance alarms and ensures stable control. Process alarms are organized into a 4-level hierarchy: high HH, high H, low L, and low LL. HH and LL are urgent safety integrity level alarms that trigger immediate shutdowns or equipment trips. H and L are high priority warnings, giving operators time to respond before a trip occurs. Setting these limits correctly is vital for both safety and operational efficiency. Guide recommends setting the high H warning at 85% of the high HH trip value. This gives operators a clear early warning before a critical condition occurs. Proper configuration of alarm limits ensures that the plant can respond quickly to abnormal situations, minimizing risk and downtime. Let's walk through a real-world example. Suppose you have a pressure transmitter with a 420 MA output, representing 0 to 16 bar. Using the scaling formula, you can convert any raw value from the PLC into a precise pressure reading. This step-by-step calculation ensures that the displayed value on SCADA matches the actual process condition. Next, consider a temperature transmitter with a 420 MA signal covering 0 to 200 degrees C. By applying the same scaling formula, you can translate the raw PLC value into an accurate temperature reading. This process is vital for maintaining precise temperature control in critical operations. For level measurement, a radar transmitter might output 420 MA for a range of 0 to 100%. The scaling formula converts the raw value into a percentage, allowing operators to monitor tank levels accurately and avoid overflows or shortages. A magnetic flow transmitter might use a 420 MA signal to represent 0 to 500 M3/HR. The guide explains how to use scaling and a totalizer to accumulate flow volume over time, providing operators with both instant and cumulative flow data. The SCADA value reads exactly double or half of what's expected. The most likely cause is an incorrect Ng max parameter in the PLC. For example, if the range should be 016 bar but ENG max is set to 32 bar, the displayed value will be twice what it should be. Always verify your scaling parameters to avoid this common pitfall. Sometimes the displayed value is consistently offset by a fixed amount. This usually means the ENG min parameter is incorrect. For instance, if the scaling assumes 0 to 100 instead of -40 to 85, every reading will be off by a constant value. Double-check your ENG min and ENG max settings to ensure accurate scaling. If you see negative values where you expect only positive readings, it's likely that the min and max parameters have been swapped. This mistake reverses the scaling, causing the output to decrease as the input increases. Always confirm the correct order of your scaling parameters. If the value reads correctly at the endpoints 4 MA and 20 MA but is wrong in the middle, you may have applied or omitted a nonlinear scaling function such as square root extraction. This is common in flow measurements. Make sure you're using the correct scaling method for your application. If the displayed value jumps erratically, the signal may need additional filtering, or you might be seeing analog to digital converter (ADC) quantization noise. Applying a suitable filter can smooth out these fluctuations and provide a more stable reading. Before commissioning any analog signal, it's essential to follow a thorough verification checklist. This ensures that both the math and the physical wiring are correct, preventing costly mistakes and downtime. The checklist covers everything from transmitter nameplates to alarm testing. Start by checking the transmitter nameplate for the correct range and signal type. This simple step can prevent many configuration errors. Make sure the instrument matches the expected input for the PLC and SCADA system. Inject exact 4, 12, and 20 MA signals into the input to verify the minimum, midpoint, and maximum readings. This step confirms that the scaling is correct across the entire range, not just at the endpoints. Confirm that underrange and overrange alarms trigger as expected. This ensures that the system will respond appropriately to abnormal conditions, protecting both equipment and personnel. Finally, make sure the values displayed on SCADA screens match those in the PLC with no double scaling or mismatches. This final check guarantees that operators are seeing accurate, real-time data for decision-making. Scaling isn't just theory, it's applied every day in process plants. Whether you're configuring a new transmitter or troubleshooting an existing loop, understanding scaling ensures reliable operations. Let's look at how these principles are applied in real-world scenarios. Proper setup of field instruments is the first step in accurate signal processing. This includes wiring, configuration, and initial calibration. Each step must be performed carefully to ensure the analog signal is correctly interpreted by the PLC. Configuring the PLC's analog input module is critical. You must select the correct signal type, range, and scaling parameters. Any mistake here can lead to incorrect readings and potential process upsets. The SCADA system must be configured to display engineering values, not raw integers. This involves setting up the correct scaling and units for each signal, ensuring operators see meaningful data. Many PLCs use function block diagrams (FBD) for signal processing. The scaling logic is implemented as a block, making it easy to visualize and troubleshoot. This graphical approach helps engineers quickly identify and correct errors. For more complex applications, scaling can be implemented in structured text (SD) code. This allows for advanced logic such as custom filtering or nonlinear scaling, tailored to specific process requirements. A totalizer is used to accumulate flow volume over time, converting instantaneous flow rates into cumulative totals. This is especially useful for tracking production or consumption in process plants. Accurate documentation of scaling parameters, alarm limits, and filter settings is essential. It ensures that future troubleshooting and maintenance can be performed efficiently, reducing the risk of errors. Clear communication between engineering, operations, and maintenance teams is vital. Everyone must understand how signals are scaled and what the displayed values represent to ensure safe and efficient plant operation. Some of the most common mistakes in analog signal scaling include incorrect parameter entry, double scaling, and ignoring signal noise. Being aware of these pitfalls helps prevent costly errors and ensures reliable data. Analog signal processing is not a set-and-forget task. Regular reviews and updates to scaling, filtering, and alarm settings are necessary as process conditions change. Continuous improvement keeps the system accurate and responsive. Proper training in analog signal scaling, filtering, and troubleshooting is essential for all automation personnel. Investing in skills development ensures that your team can handle any signal-related challenge with confidence. Industry standards guide the configuration and scaling of analog signals. Following these standards ensures compatibility, safety, and ease of integration across different systems and vendors. As digitalization advances, analog signal processing continues to evolve. New technologies like smart transmitters and advanced analytics are making scaling and troubleshooting more automated and reliable than ever. To sum up, accurate analog signal scaling is the backbone of safe and efficient process automation. From raw values to engineering units, from filtering to alarm configuration, every step matters. Mastering these concepts will help you keep your plant running smoothly and safely. Apply these principles in your daily work. Whether you're commissioning new equipment or maintaining existing systems, a solid understanding of analog signals and scaling will make you a more effective automation professional. Stay updated with the latest best practices and technologies in analog signal processing. Continuous learning ensures you're always prepared for new challenges and opportunities in automation. Work closely with your team and share knowledge about scaling, filtering, and troubleshooting. Collaboration leads to better solutions and a safer, more efficient plant. Remember to always use the verification checklist before finalizing any analog signal configuration. This simple habit can prevent major issues and ensure your system operates as intended. Analog signals and scaling are fundamental to process automation. By mastering the concepts in this chapter, you're building a strong foundation for your career and contributing to the safety and success of your plant. Keep learning, stay vigilant, and always strive for excellence.